Hello. So a neutron walks into a bar and orders a drink, and the neutron says to the bartender, "How much?" And the bartender, of course, says, "For you, no charge." Okay, we're going to talk about the fourth lesson in topic 8. And to be quite honest, this lesson here is pretty much just review of things that we've learned all year long. So we're going to talk to you guys, introduce you about the law of conservation of mass. But we're going to be reviewing things like how to name ionic compounds, diatomic elements, what they are, balancing equations, gram-mole conversion practice. So we're going to be doing pretty much practice. There's not really much new here besides just a quick definition of the law of conservation of mass. So this is a nice review. Good practice in honing your skills in chemistry here. So let's get started. If I took a vial and I put a match in it and I increase the temperature inside the vial to its ignition temperature, so without striking it or anything like that, it just auto-ignited, and the match was to burn out inside the vial. A classic question is which one of these vials would have more mass, which one would be heavier? And a lot of people will instinctively look at this and say, okay, well, I know a match is heavier than ashes of a match, and so a lot of people would think that maybe in vial A would have more mass than vial B. But the reality is that the mass in A and B are equal to each other, because although the solid in A there's more solid in A than there is in B, the gas in A is lighter. So when you burn this, you have heavier gas, because the law of conservation of mass, it states that matter cannot be created or destroyed. Mass cannot be created or destroyed. Solids, liquids, and gases all have mass, and a lot of people kind of just forget that gases have mass. They think, okay, well, solids have mass and liquids have mass, but if they were to change into a gas, we say it like disappeared. But that's not true. Gases have mass too. So things don't gain or lose mass. They just can change states. They can change forms. So, practice. And this is a really good lesson to have a calculator out and have a periodic table out. Pause this video and practice. This is really about practicing. So, this is not meant as an introduction to teach you these things. I'm just giving you a warning. This is meant as practice. You should have a good concept of these things that we're talking about here. So the first thing I'm going to have you guys do is write this equation in symbols. So how can you write this? Iron reacts with oxygen to produce iron 3 oxide. I would pause the video and give this a try. Iron reacts with oxygen to produce iron 3 oxide. All right. To do this, we need to write it out in symbols. We know that iron has a symbol of Fe, and it reacts with oxygen. If it's going to react with something, we use a plus sign, and we're going to react with oxygen. We remember that oxygen is a diatomic element, along with the other 7 diatomic elements. And let me just put a periodic table over here and review our diatomics together real quick. Our diatomic elements we have hydrogen is diatomic, and there's 7 of them, and the other 7 make a 7 at the end of your periodic table. We have nitrogen, oxygen, fluorine, chlorine, bromine, iodine. It makes a 7 right here. 7, and don't forget your hydrogen. So these are our diatomics. These elements, when found as in their elemental form, will always come in pairs. So that's why it's O2. And it's going to produce, so we're going to put the yield sign, iron 3 oxide. So it's going to produce iron 3 oxide. And produce means I put an arrow here, so that could be produce or yields or makes, anything like that. That's what this is saying here. So iron reacts with oxygen and it produces iron oxide. But iron 3 oxide, what is iron 3 oxide? let's go real quick again about learning how to do our ionic compounds. Iron 3 oxide, iron 3 oxide means that 3 means that that 3 means that the charge of the iron is +3. So that's iron 3, and oxygen on your periodic table, you should look on the periodic table and you see that it is 2 spaces away from a noble gas, and that's for its -2. It's going to need 2 electrons to get a noble gas configuration. And so to figure this out, we could just cross these charges so that they equal each other. So it would be iron, there's a 2, and oxygen, there's a 3. So that would be the formula for iron 3 oxide. Good, we did it right. So that's how we would write this in symbols. The next challenge that I'd like you to do is try to balance this equation. So pause the video and see if you can balance this equation. Okay. The first thing I do when I balance equations is I list all of the atoms that are in the equation. I've got iron and I've got oxygen, and then the second thing I do is I'm going to count them. I've got 1 iron, 2 oxygens, 2 irons on this side, and 3 oxygens on this side. I'm going to try to balance these one at a time until the whole thing's balanced. Now the problem is I can see already, and if you tried this and paused the video, you might have seen this problem too, is that the oxygen on the reactant side has to be a multiple of 2, but the oxygen on the product side has to be a multiple of 3. So the least common multiple that 2 and 3 can both go into is 6. So if I put a coefficient of 3 in front of the oxygen, that gives me 6 oxygens on my reactant side, and now I can try to balance my oxygens on my product side by putting a 2 here. I now have 6 oxygens, but that changed my irons to 4, so I've got 4 irons and 6 oxygens here. Now my oxygens are balanced. Now I can easily balance my irons by putting a coefficient of 4 in front of the iron. So now we've balanced this equation. Okay. The next thing I want to have you guys do, so we're doing all kinds of different skills here, is would you pause the video and convert, so I'm asking you 3 problems right now. Convert 4 moles of iron into grams. Then convert 3 moles of oxygen into grams. Convert 2 moles of iron 3 oxide into grams. I'm just using these coefficients as my number of moles, because what this is really saying is 4 moles of iron plus 3 moles of oxygen yields 2 moles of iron 3 oxide. So let's convert those all into grams. So pause the video and see if you can do that. What you should have done is to convert 4 moles of iron, we need the molar mass of iron, and that's in grams per mole. I set it up to cancel, so my moles cancel my moles. I don't divide, I'm going to multiply so that I can cancel out those moles. And I've got 223.4 grams of iron, converting 4 moles of iron into grams. If this is very unfamiliar to you, please go back and review topic 8, lesson 1. That's where we go over how to do this stuff. The second one, let's convert 3 moles of oxygen into grams. So 3 moles of oxygen, and 1 oxygen consists of O2, means that there's 2 oxygen. The molar mass of O2 is the sum of an oxygen plus an oxygen. So please set it up this way. So 3 moles of oxygen times the molar mass of O2. And when we do that, you come up with 96.00 grams of oxygen. Now let's do the last one here. 2 moles of iron 3 oxide. Let's convert 2 moles of iron 3 oxide into grams. So I've got 2 moles of iron 3 oxide, and the molar mass of iron 3 oxide is the sum of 2 irons plus 3 more oxygens, and that's how I got that 159.7. That would be if you sum up the molar mass of 2 oxygens and 2 irons and 3 oxygens. And we multiply this by 2, converting out, and I've got 319.4 grams. It would be the molar mass of 2 moles of iron 3 oxide. So that would answer this question here. The final thing I want you to do is compare the mass of your reactants to the mass of your products. So if we take a look at those masses that we had for our reactants, this was our iron and our oxygen, and we sum those together, and there's only one product, so we don't have to add anything here. You should find that the mass of your reactants will always equal the mass of your products. So what we just did here was a series of steps, and we proved the law of conservation of mass in formulas here. So by mass, in this side here versus side here, the mass will be equal to each other. So the total mass of reactants equals the mass of a product as predicted by the law of conservation of mass. So this is just great review practice. It makes you balance and think about a whole lot of things in doing this here. So I'm going to have you guys do a few more of these for our workshop practice. And what I want you to do is prove the law of conservation of mass. So you're going to convert, in this first example, you would convert 1 mole of N2 into grams and 3 moles of H2 into grams. And you're going to compare that to 2 moles of NH3, which is ammonia. So nitrogen plus hydrogen yields ammonia. And so you're going to show that the sum of these two is equal to the sum of these two. We know the sums are equal. This is all about showing your work. This is all about units and showing your work. It's the process that we're practicing here. So please show your work. It gets a little more challenging as we move down. And the fourth one, you have to, it's in words, you're going to have to write the equation, and then you're going to have to balance the equation, and then you're going to have to show the law of conservation of mass for the fourth one. It's actually not as hard as it sounds. So give those a try. Oh, by the way, there's one more thing in here that you may not, that I want to start getting used to seeing, is these parentheses afterward. When you see a parentheses after an element or a compound, this is telling you the state of matter that it's in. It's not, it doesn't change anything, and if you want in your work to leave it out, that's fine, but I want to get you used to seeing this because the next lab we do, we will have change of state going on in the lab, and these symbols are important in that next lab. So I just kind of want to introduce you to it. So it's just nitrogen plus hydrogen makes ammonia, but this G, it's a state of matter, means gas. So this is nitrogen gas reacts with hydrogen gas, making ammonia gas. AQ means aqueous, something that's dissolved. So if you take like a salt and you put it in water, it dissolves, it disappears. It added to the mass of the water, but you don't see it anymore. It's in a different state. That's an aqueous state. So things that are aqueous are solutions that are dissolved in water. So we have these two solutions reacting together to make another solution and producing L, which would be a liquid water. S would stand for solid. So we have a solid that we put into a solution. It makes a different solution and produces a gas and a liquid. So this is interesting. By showing these subscripts, I can see something here. I can kind of visualize what's happening. I'm going to put a solid into a solution, and it's going to make bubbles, and those bubbles are going to be N2O. So it just tells you a little bit more what's going on. It doesn't change the calculations. It doesn't change balancing. It doesn't change anything like that. It's just letting you know the state of matter. So some equations will have them, some will not. Our next lab, these symbols will be relevant. So anyways, good luck with this. Save your questions for me, and next class, I look forward to seeing you guys and talking about what you've learned and what you need help with. Talk to you soon. Bye.